Hi, welcome back to Statics 1. Today we're going to be talking about 3D equilibrium problems. Up till now we've been dealing with 2D problems on a plane. So we had problems such as, over here, a beam and some forces, and then we had some supports like a hinge and a roller. And we drew the free body diagram in 2D, and then we calculated the forces and the moments. In this case, the moments are going to be coming, if this is in the XY plane, then the moments will be coming out of the board in the Z plane, in the Z direction of the Z axis. Now we're going to be dealing with 3D problems, and in order to do so, we have to introduce some additional support types. And they're not additional support types for the most part, but they are kind of novel representations because we have to represent the forces in 3D. And remember, whenever you have a support providing a force, it's resisting the motion. That's why for a hinge, for example, there's no resistance to the motion in the a rotational moment here. That's why there's no moment associated with that. So wherever you have a moment associated with a support, it's essentially preventing rotation. All right, so let's look at a few of the support reactions in 3D, and a lot of them are the same as the ones that we saw in 2D. So I'm going to start with a roller or a rocker. And in 2D or 3D, it's basically the same. I'll draw it like this. Let me see how I want to see how they draw it in the textbook. Pretty good. Okay, so in this case, we have one force. The force is in the perpendicular to the surface that it's resting on. So for example, if we had the surface here, then to draw the free body diagram, will be just that, just a single force upward. So that's no different than what we had before. This implies that you have a smooth surface, so you could actually move this if this is in the Z direction out of the board, we can move it in the Z direction. So it's a roller, a rocker. It could also be just a smooth surface. So you could just have, instead of having a roller, you could just have some kind of a member on essentially idealized as a smooth surface. Obviously, we know there is friction going on there. The second one, and this one's kind of novel. We don't see this one in 2D. Can't imagine how you could. I guess you could, but I'm not sure. And I'm going to draw. It's called a ball socket. So you can imagine it's kind of like your shoulder, in that there's no resistance to rotation, but you can't pull your shoulder out of your arm, you can't move it up, and you can't move it forward. So it's providing translational forces, but no moment. So let's see if I can draw this. They typically draw it like that. And then there's a ball in here, and it's attached to the member. Well, hopefully you kind of get the idea. And this would be like basically attached to the some kind of a fixed support, a fixed wall or floor, and it has forces. If we draw the free body diagram, and I'm going to put Z in the vertical direction and X and Y. Remember our right-hand rule, so that works. And then we're going to have a force, and I'll do the forces in another color. The force would be F of X, F of Z, and F of Y. Hopefully this is somewhat intuitive, that you kind of get it. So let me put this here. So in this case, we just had an F of Z. All right, the third one I want to talk about, and this is also, we do see this one in 2D, and it's a fixed support, and I'm going to put it right here. Fixed support. And you remember fixed support is essentially, I don't know how else to put it, but super glued fixed support. Super glued to the wall, so it's not rotating and it's not translating. In fact, it's not rotating in 3 directions and not translating in 3 directions. Kind of like, if you want an analogy, it's like your nose. You can't rotate your nose in any of the 3 directions, and you can't pull it off of your face and move it off your face. So that's a fixed support. And let's see how they draw it in 3D, or if they even bother. Nope, actually, they show it like this in the textbook. So here it is, super glued down here. So the free body diagram. So again, I'm going to have a Z direction, Y direction, X direction. And here's one we're going to see something a little different. We're going to see 3 forces, just like we had with the ball and socket. So we're going to have F of Z, F of Y, and an F of X. But it's also, this one did not resist rotation, but this one does. So we're going to have 3 moment vectors. And I'll do them in red, why not? And they're always counterclockwise. So let's see if I can draw this correctly. 1, and we have 1 here. So this would be the M of Y. This one is M of Z. And then M of X will be over here. And I want to draw it that way. This one will be M of X. Okay, so that's our fixed support. Resist has essentially 6 support reactions. I'll write that down. So this one has 6 reactions. This one has 3. And this one has just 1. All right, let's see what else we have for support reactions of interest. Oh, there is a pin or a hinge, and I'm going to put it, so the next one I want to talk about is a pin or a hinge. And we've seen a pin or hinge in 2D, but now in 3D, it's kind of the same, except now it's resisting, it allows rotation in the direction that it's supposed to, but it's resisting rotation in the other axes. So let me see if I can draw one reasonably well. And I'll draw both a pin and a hinge, and they're both basically, they have the same support reactions. So this is either a pin or a hinge, and it looks like, kind of like this. And I'll put X direction, Y direction, Z direction, and it looks like, see if I can draw it like that. Let's do it in a different color. I'll do it in green so it'll stand out a little bit. And then there's another side to it over here, right? And there's a pin going through the center, and then the member is in between this. So you can see that it allows rotation in this direction, which would be in the Y direction. In this case, and obviously I could have drawn this differently, but in this case, it's allowing rotation for the X moment. In other words, there is no X moment because it's allowing rotation in that direction, but there is a Y rotation, Y moment, preventing rotation this way, or certainly like to twist it from the top. So the free body diagram for this would look like, I'll do it here. Here again, here's our axes, X, Y, and Z. And this one will certainly have forces in all 3 directions because it's bolted down, right? It's not moving. So it has forces in all directions, force in the Z direction, force in the Y direction, force in the X direction. But it's only going to have 2 moments in the Y direction and the Z direction, but not in the X direction because in this case, it's allowing rotation in the X direction. So I'll put a moment over here and one over here. So now you can see we have 5 support reactions. And a hinge, which I dare to, do I dare to draw it? Try to draw it? I'll draw one. Imagine we have a hinge. The hinge will be similar. The moments, the response forces are similar or identical. So here's the bottom of my hinge. Those are screws that would screw it into a door, for example. And then how do I draw this in 3D? Let's try. Here's the upper part of the hinge. Oh well, it's not too bad. So this can collapse down. Same as this one. So we have X. There's no moment in the X direction, but there is a moment in both the Y and the Z direction. So this would have the same free body diagram as the pin. There are some other ones. Let me get this one. It's called a single. Now we're getting into kind of the realm of mechanical engineering. And I'll just give one of them. I'll give the journal bearing. There are others in that you'll see in the textbook, but I'm just going to give these 5. So you have a journal bearing. So what the heck is a journal bearing? It's not something, I suppose there might be a civil engineering application for it. But in this case, it looks kind of like, bear with me, see if I can draw this correctly. Oh, that's pretty awful. And then I'm going to try and do it in 3D. Good. All right, not terrible. So there's a shaft goes through this thing. The shaft's allowed to move. Let's finish this off. The shaft can move in and out with no resistance to force, but in the other directions, it is constrained. So if there's a shaft coming out of this thing, how do I draw it? I'll draw it like that. All right, well, that's pretty good. So you have this shaft in here. The shaft can go in and out, but it can't, and there's no resistance to it turning, but there is resistance to rotation in this way or this way, right? And obviously in the force as well. So the free body diagram, this will be my last one. Z, Y, and X. Let's see if I can remember this. So it has a force, depends how you orient this thing. Let's imagine that I've oriented it where this is essentially in the Y direction. So I'm going to turn it. So it means there's no force in that direction, but there is a force this way. There's a force in the Z direction, a force in the X direction. And there are 2 moments that could be exercised, not in the Y direction, but there's one in the X and one in the Z. And I'll do those in red as I've been doing them. So that's my moment in the Z direction and my moment in the X direction. And obviously any of these could be turned in some other direction. So this one could have had, in this case we had the hinge aligned with our X-axis. We could have redrawn this with the hinge aligned with the Y-axis, or the Z-axis for that matter. So what else? I wanted to tell you how many reactions. So this one is 1, 2, 3, 4 reactions. And this one has 1, 2, 3, 4, 5 reactions. 5 support reactions. Probably it's a good idea that you know all of these. Maybe, this one, probably it'd be okay, like if I said it was a journal bearing, that you would look it up and understand how to interpret this free body diagram. All right, so the way you solve these problems is similar to the way you solve the 2D problems. We're going to set up our equilibrium equations. So we're going to sum the forces and we're going to set them to 0. We're going to sum the moments to 0. The only difference is, in this case, in addition to the force in the X and Y direction, we have a force in the Z direction. And in addition to a moment, and previously we only had the moment in the z direction, now we're going to have moments in the x and y directions. So we now have 6 equations. So essentially, when you draw a 3D diagram structure, if we have 6 equations, we can solve for the value of 6 support reactions in response to some kind of a loading. So I think what I'll do now is stop, and we will, in the next video, what I'll do is describe an example of how we evaluate the support reactions in a sort of a typical 3D problem. All right, so that's it. I'll see you in class. If you have any questions, please give me an email.